Hello maths fans, Dr Tom Crawford here at the University of Oxford, and today we're continuing the Oxford Linear Algebra series by looking at eigenvalues and eigenvectors of a matrix. Eigenvalues and eigenvectors are incredibly powerful tools, and we'll see examples of why later in the course, but in general they allow a matrix to be reduced to a much simpler form, which makes further calculation much easier. In essence, they reduce a matrix to a number via the following equation. If A is our matrix, V is the eigenvector, we want to solve this is equal to lambda times V, where lambda here is the eigenvalue, and as I said, V is going to be our non-zero eigenvector. Looking at this equation, you might be thinking, well, how on earth do we solve this? We want to replace a matrix by a scalar, by a single number. And the trick actually lies in determinants. But before we get to that, we can start by rearranging the equation. So if I take this over to the left-hand side and we factor out V, then I can say A minus lambda times the identity matrix, so that A minus lambda makes sense, multiplied by V has to be equal to the zero vector. So now we have two terms, when multiplied together, that need to equal 0. So we can proceed in the usual manner and say, well, suppose V is 0. This is our first option. So V could be 0, and then this matrix multiplied by 0 definitely gives me 0. And this is why we actually specify here that we want a non-zero eigenvector. Because if it's 0, it's kind of boring, and the whole equation is obviously true. Matrix times 0 vector equals number times 0 vector. They're both 0. So instead, we proceed by saying we want this to be equal to 0. Now, if A minus lambda I is 0, that means our matrix A is equal to lambda times the identity matrix. But then that really limits the type of matrix A that we can actually investigate. Because this says the only way this can be satisfied following this method is if A is actually just a multiple of the identity. So it would just look like, for a 2 by 2 case, something like this. Very boring, and again, not really what we're interested in. We want to look at general matrices A. So what we do instead is actually go back to the equation in this form. And what we can say is, if the inverse of this matrix exists, so if I say, supposing A minus lambda I, which is of course a matrix, supposing that has an inverse, and we'll talk about the condition on that in just a moment, but supposing it has an inverse, then I can rearrange this equation and say, well, V has to be equal to the inverse of A minus lambda I, so we'll put a minus 1 there to signify the inverse, multiplied by 0, and now we have a matrix multiplied by 0, so it's 0, and again we're back to the boring case, or the case we're not actually going to allow, of V being 0. So in both situations, from this equation here, we have two terms multiplied together to give us 0. If we follow the traditional route of two things multiplying together equals 0, means each one of them individually could be 0. We don't want V to be 0, that's boring. And if we set A equals lambda I over here, that's also boring. So if this has an inverse, we can then multiply both sides by the inverse, and we again get V is 0. So the only way we can actually have something interesting, the only way we can, it turns out, find a non-zero V, is if this matrix, A minus lambda I, does not have an inverse. So we're actually interested in answering the question, when does A minus lambda I not have an inverse? Because if it does not have an inverse, then we cannot pre-multiply by that inverse, and so therefore v is not 0. And so we actually have a chance of finding v. So it all comes down to this. When, or what is the condition on A minus lambda I for it to not have an inverse? Now, we've talked about inverse matrices in earlier videos in the Oxford Linear Algebra series, and we actually saw the condition to not have an inverse is exactly when the determinant of A minus lambda I is equal to 0. So this is the equation that we actually solve to find the eigenvalues lambda. And this is called the characteristic equation. So just to recap, we solve the determinant of A minus lambda I equal to 0. That will give us an algebraic equation for lambda. It will give us a polynomial in lambda. We solve, find those roots to get lambda, the different possible eigenvalues. So this gives us the eigenvalues. And once we have the eigenvalues lambda, we go back to our equation at the top. Here we substitute in for lambda, and then we can solve for our eigenvector v. Now, before we go through some examples together, I do recommend checking out the video lectures on this topic from ProPrep, which are linked in the video description. ProPrep is an online resource that provides customized tutorials for students looking to improve their skills in STEM-based subjects. There is almost 2 hours of content looking at eigenvalues and eigenvectors, which will really help you to understand the topic. You can access the videos by signing up for a free trial using the link below. Let's look at an example to see how this works in practice. Suppose I want to find the eigenvalues and eigenvectors of this 2x2 matrix A. So we want to solve the equation A times a non-zero vector V is equal to a scalar lambda, which is the eigenvalue, times the same non-zero vector. Now our approach, as we've just seen, is to calculate or solve the characteristic polynomial, which is the determinant of A minus lambda I is equal to 0. So here we have a 2x2 matrix. So lambda times the 2x2 identity will give me 5 minus lambda in that first entry, minus 3, because there's a 0 in the identity matrix there. That stays as 1, and then this becomes 1 minus lambda. And we want the determinant of this to be equal to 0. Now this is a 2x2 matrix. The determinant is just the diagonal ones minus the off-diagonal product. So we can say that's equivalent to 5 minus lambda times 1 minus lambda minus 3, so plus 3 equal to 0. So we're going to need to expand this bracket, which gives us 5 minus lambda minus another 5 lambda minus 6 lambda plus lambda squared plus 3 equals 0. So that becomes lambda squared minus 6 lambda plus 8 is 0, and that factorizes really nicely into lambda minus 4, lambda minus 2 equals 0. So lambda is 4 or 2. So our eigenvalues here are lambda equals 4 and lambda equals 2. Now just to say for this step here, I was able to spot that this factorizes really nicely. Of course, they won't always factorize, and you can use the quadratic equation here to solve for your roots lambda. So we now know the eigenvalues are 4 and 2. So following our method, we now have to plug them in to our equation to actually find the eigenvector v. And here we're considering a general v, which has to be 2D. So v here is going to be x, y. And we need to find the direction of this vector. Now there's an important thing to spot at this point in the calculation, which is to say if v, some vector, satisfies this equation once we've fixed lambda, then in fact any multiple of v will also satisfy this equation. Because if I simply replace v by alpha times v, then my equation up here just becomes alpha av equals alpha lambda v, so I cancel the alpha and the same equation is satisfied. So when we're looking for a general v, we have some freedom in multiplying the whole thing, both x and y, by the same constant number. And that's important to remember. We're actually just interested in the direction of this vector. So if you were to plot this like a triangle, you would have a fixed angle because it would be the ratio of these that would be equal to tan theta, and so multiplying by this constant alpha wouldn't affect that angle, and so the direction would be the same. If we start with lambda equals 4 and we substitute lambda equals 4 into our eigenvalue equation for this general v, then what we have is 5 minus 3, 1, 1 times xy has to be equal to 4 times x, y. So now we can expand this out. So the first row is going to give me 5x minus 3y has to be equal to 4x. And the bottom row says x plus y is equal to 4y. So rearranging the second one, this tells me here that I can say x therefore is 3y. And then in this top equation, I can also take the 3y across, subtract the 4x, and that also gives me x equals 3y. And the reason we have the same equation is what I was just talking about regarding we can multiply v by some constant alpha. So you'll find that your rows in your eigenvector equation will actually be multiples of one another in a lot of cases. So we're free to pick one of the values for x or y. So to make things easy for ourselves, I'm going to let y be equal to 1. And then in order to satisfy this equation, I need x to be equal to 3. So this gives me my eigenvector for the eigenvalue of 4 to be given by 3, 1. Now, of course, it's always worth checking your answer. You want to make sure that these values of x and y satisfy the simultaneous equations. Unfortunately, we can see that they do, because 5 times x gives me 15, minus 3 equals 4 times 3, which is 12. And similarly, x plus y, that's 4, equals 4 lots of 1, which is also 4. So for the eigenvalue of 4, we have an eigenvector given by 3, 1. The calculation for our second eigenvalue is very similar. So we begin by saying when lambda is 2, we want to satisfy this equation. So that says 5 minus 3, 1, 1 times xy needs to be equal to 2 lots of xy. As before, we expand this out. So we get our simultaneous equations. 5x minus 3y has to equal 2x. So I can immediately see that's going to tell me that x is equal to y. And the second one tells me that x plus y has to be equal to 2y, which also, when you subtract y from both sides, gives me that x is equal to y. So we can pick any value, we keep things simple, we say let x equal 1, then y is also 1. So our eigenvector for the eigenvalue of 2 is given by 1, 1. So it's a line with a 45-degree angle. And that's it. We found both eigenvalues by solving our characteristic polynomial. The determinant of a minus lambda times the identity had to be 0. This gave us a quadratic equation. We could factorize it here or use the quadratic formula to get the solutions that lambda must be 4 or 2. These are our eigenvalues. We then substitute those in one at a time and solve for a general vector xy to find when we have an eigenvalue of 4, the vector is 3, 1. And when we have an eigenvalue of 2, v is given by 1, 1. And of course, both of these are non-zero, so therefore they are valid eigenvectors. Now let's look at an example with a 3 by 3 matrix given by A is equal to 2, 1, 2, 0, 0, 1, 0, 1, 0. As before, we start by saying we want to find non-zero v and lambda such that A times the vector v equals lambda times the same vector v. And again, we need to solve the characteristic polynomial, which still says that the determinant of A minus lambda I has to be equal to 0. So our matrix now becomes 2 minus lambda, 1, 2. Then we get 0. This one now has a minus lambda and a 1. And on the bottom, 0, 1 minus lambda. And we need to solve this 3 by 3 determinant equal to 0. Now looking at the matrix, the form of the matrix that we have, we can see that this first column contains a lot of zeros. And we talked about this in the earlier determinants video. I think this was video 2 or 3 in the Oxford Linear Algebra series. And we said that when you have lots of zeros in a row or column, it's a good idea to expand in that row or column because it simplifies the computation. So if we expand in the first column, then we only actually have one non-zero term, and that's 2 minus lambda, which is then multiplied, crossing those off, by the remaining 2 by 2 determinant. So multiplied by the 2 by 2, which is minus lambda, 1, 1, and minus lambda. And we need that to be equal to 0. So expanding this out, we've got 2 minus lambda. We've then got minus lambda times minus lambda, so that's going to give me a lambda squared minus 1 times 1, so minus 1. So this is now our characteristic equation, our characteristic polynomial for this particular matrix. Now we can actually see what these solutions are immediately because the equation has already been factorized. So this tells us that lambda is equal to 2, and then we can have plus 1 or minus 1. So we get 3 eigenvalues because we have a 3 by 3 matrix, 3 eigenvalues, and exactly as in the previous example, we now take these in turn, substitute them into our original equation, and solve for the eigenvector v, where remember now, v will be a general 3 vector. So it will be x, y, and z. Starting with lambda equals 2, we now substitute into our equation, and we have to solve 2, 1, 2, 0, 0, 1, 0, 1, 0 times x, y, z has to be equal to 2 lots of x, y, z. Again, we now expand row by row. Now if we take the third equation, y equals 2z and substitute into the equation above, this will actually tell us that z has to equal 4z. So the only way that can be true is if z is 0. So this tells us that z is 0, but then y is 2 lots of that. So y is also 0. And then going back to our original equation, y plus 2z is also 0. So x is undetermined, y and z both have to be 0. So our eigenvector, writing it as simply as possible, is going to be 1, 0, 0. We have to have y and z being 0, otherwise the equations are contradictory and we can't have that. So they have to be 0. X can be anything. Let's just pick it to be 1 to make it nice and easy, and so we actually get the unit vector along the x-axis. We do the same for the next eigenvalue, which here is lambda equals 1. So when lambda equals 1, we substitute into our equation. So we have 2, 1, 2, 0, 0, 1, 0, 1, 0 times x, y, z needs to be equal to 1 times x, y, z. Expanding that out. So the last two equations are now consistent. We saw last time they weren't, which meant both variables have to be 0. These are now actually telling us the same thing, and so we substitute that into our top equation and subtract an x from both sides. We can now say that y plus 2y plus x has to be equal to 0. So we can say that x is in fact equal to minus 3y, which is the same as minus 3z. As before, we are free to choose the value of each of these variables, provided this equation remains satisfied. So I think here, picking y and z to both be minus 1 is going to be helpful. So for v, if I pick y to be minus 1 and z to be minus 1, then they are certainly equal. And I've now got that x is equal to minus 3 times y. So minus 3 times minus 1 gives me 3. So the eigenvector here is going to be 3 minus 1, which corresponds to the eigenvalue of lambda is equal to 1. Finally, for our third eigenvalue when lambda is minus 1, we again substitute into our original equation, and we're going to have to solve 2, 1, 2, 0, 0, 1, 0, 1, 0 times x, y, z equals minus x, y, z. Again, we expand this out. Again, these two equations are indeed consistent. It just says that whatever we pick for y, z is the negative of that, and vice versa. So they're fine. Now substituting those into the top equation, so I'll take this one and plug it in here. I can say, adding the x across, 3x plus a y, which is a minus z, plus 2z has to be 0. So I can in fact say that 3x has to equal z. And from there, I can say y is equal to minus z. So I'm going to start by picking x to be equal to 1 and then making sure I can satisfy both of these equations. So if I pick x to be 1 to hopefully simplify the eigenvector, we'll see, then if x is 1, that tells me that z is 3. And then y has to be minus z, so y has to be minus 3. So for the eigenvalue of minus 1, we get the eigenvector 1, minus 3, and 3. And we're done. We've found 3 eigenvalues, lambda being 2, 1, and minus 1. These are the solutions to our characteristic equation or characteristic polynomial, where we solve the determinant of a minus lambda I equal to 0. We found the eigenvalues as the roots of that equation. we've then substituted in to our original expression that we wanted to solve for lambda and v. And now that we know lambda, we can substitute in one by one to find the general form of the eigenvectors. As before, make sure you check your answer, take these values of lambda and v, substitute them into this equation, and make sure that I haven't made any algebraic slips. These calculations can be quite complicated, so I really do recommend substituting back in at the end to make sure your solution is correct. And for more practice exercises and videos with step-by-step breakdowns of the solutions, once again, I recommend heading over to ProPrep. There are 15 exercises for you to check out, beginning with some computational questions similar to those we've looked at here, before moving on to some proofs and a discussion of the properties of the characteristic equation. Remember to sign up using the link in the video description for a 30-day free trial with full access to all of the videos. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all soon. Take care.